All right, so
Okay.
welcome everyone to this global non-commutative geometry seminar. Actually, welcome from Paris, so where Alain Connes is, but also myself, although not at the same place. So this will be the final talk this semester for the global non-commutative geometry seminar of the European of Europe and Asia. And maybe also of a kind of the last one in a series where we had these kind of bi-weekly and last year even weekly meetings. And that will kind of be transformed next year into a form which was a term coined by Gianni Landi, à la carte. So this, one never knows, in fact, that maybe we were just discussing this, that eventually we will get back to the kind of regular meetings. But since right now, at least, many people have activities, it's very hard to kind of keep a running seminar like this. But who knows? We'll see. In any case, it's a great pleasure that the speaker that started this series 2 years ago, almost 2 years ago, is also giving this talk, which is Alain Connes. So, Prolate Spheroidal Functions and Zeta.
Okay, thanks a lot, Walter. So, so what I will do today is to, sort of review the whole framework of the interrelations between prolate spheroidal functions and zeta. And I mean, it's all, of course, centered around, question which has been fascinating me since almost 30 years. And I mean, my talk will be essentially, divided in two parts. I mean, in the first part, which is the joint work with Katia Consani, I will concentrate, I mean, this part will really concentrate on the low-lying part of the spectrum, I mean, of the zeros of zeta. And I mean, in particular, it will give an operator theoretic incarnation of the Riemann-Siegel formula. But I mean, I want to recast, if you want, I want to recall the main steps that we followed. And the first step is the turning from an absorption spectrum to an emission spectrum. Then a strong form of Weil positivity. Then the discovery of the minuscule eigenvalues of the Weil quadratic form. And finally, the zeta cycles and spectral triples. And I mean, in the second part of my talk, but I mean, Henri gave a beautiful talk last week in the seminar of Piotr Ayach. So, I mean, I hope I will be able to add relevant stuff to what he said, but I will sort of start from the start, if you want. So recall everything. And so this second part will handle the ultraviolet part of the spectrum, the ultraviolet part of the, if you want, the zeros of zeta, and the associated geometry. Both, of course, aspects will be deeply related to non-commutative geometry. Now, the starting point is many years ago. I mean, I think it was essentially in 1996, in fact. So what I discovered using the BC system was that one could realize the zeros of the Riemann zeta function as an absorption spectrum. So by an absorption spectrum, what it means, if you want, is that it's missing lines on background, which is the ordinary light. Now, what happens when you have this is that, I mean, it's very understandable that you can use that in order to prove the explicit formulas. And what I found, if you want, is that there was a natural space, which is the Adel class space, which is underlying, whose geometry is underlying this construction. And but somehow, if you want, even though now we understand what is the deep geometric meaning of the Adel class space and of the construction that I was doing, which was giving an absorption spectrum, this construction turns out to be related to Hochschild homology and to the trace map in Hochschild homology, as we shall show in a coming paper with Katia. But what happens, however, is that if you want, because it's an absorption spectrum, it's very hard to detect. And I had to make a cutoff. So this is the PQ plane, if you want, it is a phase space picture. So I had to make a cutoff in both space and momentum. And for that, I was using two projections. If you want, I was using the projection P lambda, which is a cutoff in space, and its Fourier transform, which is the projection in momentum space. And I mean, so this was the first meeting with Prolate functions. But somehow, if you want, what happens is that, especially because one is working in an absorption spectrum, it's very difficult to get information about the location of the zeros. And I mean, the first thing that we did with Katya in the paper which was dedicated to Dan Voiculescu, what we did was to understand that there is a way to transform the absorption spectrum into an emission spectrum. And how does this go? Well, if you want, the simple manner in which it goes is that what you do is you combine, you take the difference between white light and you subtract from the white light the absorption spectrum. And then what you obtain by doing that, you obtain an emission spectrum. But as we shall see what happens. So what happens is the following, is that the white light is very easy to understand. I mean, it's in terms of just now the cutoff is between minus log lambda and log lambda. And at the energy level, it's in the strip, which is between 0 and e over 2 pi. And then it turns out that there is a symplectic map to the PQ plane that I was talking about before, which is this map phi of uv, which is exponential of u, and v exponential minus u. I mean, it preserves the area and so on. And what it does, it essentially covers the absorption spectrum, except for some bit which is protruding. So what happens is the following, is that you see in this picture, you see the absorption spectrum, which is here, okay? And but there is a bit which is protruding, which is here. And this is, if you want, the emission spectrum. So what one does in order to see better, of course, one rescales, which is again a symplectic transformation. I mean, what you do is you divide the momentum by lambda, and you move the q, you multiply the q by lambda. Of course, this is a symplectic transformation. And what you get is the following. You get the following picture, which agrees with a picture which was obtained by Berry and Keating. And so the picture is the following. The picture is that what you have is you have the portion of the part which is below the hyperbola, which is given by PQ equals E over 2 pi, which defines the energy. But you have the constraint that Q is bigger than 1 and P is bigger than 1. Okay, except that there is a little square which escapes from this. Okay. So the next thing that we did with Katya was to say the following. Well, you see, what happens is that by the spectral realization and so on, one couldn't access to the location of the zeros precisely. But on the other hand, okay, now one has a Hilbert space, one has a very specific setup, and one should be able to attack the problem of the veil positivity, because you know what happens is that somehow one can write down a very simple equivalent of the fact that the zeros are on the critical line by saying that this quadratic form here, which is what I will call the veil quadratic form, which is the sum over the, if you want, the imaginary part of the zeros of this product for test functions f and g. Of course, I mean, saying that this is positive is the same thing as saying that the zeros are where they should be real in this formulation. Now, but what happens is that because of the Riemann-Weil explicit formula, we should think of the Riemann-Weil explicit formula as the computation of the symmetric functions of a polynomial in terms of its coefficients. So this Riemann-Weil explicit formula, which is written here, allows you to rewrite the Weil quadratic form in terms of contributions of the primes. I mean, so there is a contribution. Sorry, there is a contribution for each prime, which is given by this formula, and the most difficult, I mean, the most non-obvious contribution is the contribution coming from the Archimedean place, which is written here. It's very tricky because it has Euler constant, it has log of 4 pi, and it has a principal value in the sense of Hadamard, if you want, so that there is a divergent expression here because you have the x minus x inverse in the denominator and you integrate from 1 to infinity. And in order to eliminate this divergency, you subtract from the function these values. So it's a very tricky distribution. And fortunately, if you want, because of the equivalent kind of emission spectrum realization, what we proved with Katia, starting from there, I will explain how it goes. What we could prove is a strong form of the Weil positivity for the Archimedean place. So what it means is that you restrict the support of the test function that you are considering to be in the interval where the interval is the largest possible so that you won't have contributions from the primes. And then you want to prove that this quantity is positive, but the problem is, of course, you could do it using the computer. I mean, this is not interesting. What is really important is to find a conceptual reason why this is positive. And the conceptual reason that we found with Katia is the fact that there is an inequality between the Weil functional and, if you want, the trace of this expression, where S, what is S? So S, let's look back at the picture which I had written here. You see, I had told you that you have to take Q bigger than 1, P bigger than 1. Now, there is a beautiful space which does that, which is called the Sonin space. Okay. And the Sonin space, if you want, even though you don't have functions which are restricted, you know, with compact support in space and compact support in momentum space, what happens is that you do have many functions which have the property that they vanish identically on the interval minus lambda lambda. And so they are zero, so they can be anything elsewhere. And similarly for their Fourier transform. So this is called the Sonin space. And this picture, if you want, this constraint that Q is bigger than 1, P is bigger than 1, tells you that, okay, you should consider the Sonin space S, which is S for lambda equals 1, if you want. Okay, so that's what we did with Katia. And but now the problem is the following. I mean, you see, when I had taken the cutoff for the spectral realization, I knew, of course, that after taking the cutoff, I don't get the space which is invariant under the scaling group. So the same is true for the Sonin space, but what you can still do, even though you cannot restrict the action to the Sonin space, what you can do is compress the action of the Sonin space, and this gives you this expression. So what we proved with Katia is that it is this expression here, it is this compression of the scaling action on the Sonin space, which is responsible for the Weil positivity at the Archimedean place. I mean, the calculation was conceptual, but rather difficult, and this is a place where the Prolate spheroidal wave functions entered in an absolutely crucial manner. Namely, what we proved is in fact an equality between this compression of the trace, I mean of the scaling action on the Sonin space, and the Weil functional, but there is a difference between the two. This difference is very small. I mean, it's compact operator. It's an operator which one can control very, very well. And this operator is expressible in terms of the Prolate wave functions. So in other words, what this operator does, I mean, these are the Dirac notations where you take, you know, the brackets and so on. And there are coefficients which are coming from the eigenvalues of the Prolate wave function. So let me tell you a few words about this Prolate wave function because they will enter everywhere later. Okay, so I mean, there are these 3 papers. I should add to what I just said that, of course, you know, the natural follow-up of what we did with Katia would be to consider the Weil positivity when you consider the primes. And by the result of Weil, it would be enough, in fact, to prove the positivity for finitely many primes at a time, which is a very, very important thing because we do have the Hilbert space setup, which is ready for that. And we also have written a paper with Katia, which is called Quasi-Inner Functions and Local Factors, in which what we prove is that if you want the Sonin space, all these properties of the 2 projections and so on continue to hold when you add finitely many primes. Okay, so what are these Prolate functions? Well, they were discovered by people working by Slepian and his collaborators. I mean, in the 60s, and they were discovered because of a problem in communication of signals. I mean, so there is a paradox in the communication of signals, which is quite striking, which is the following, which is that, you know, when I am talking now, I am talking for a limited period of time, and I am using a limited range of frequencies, obviously. How can this be? Because, I mean, you know, if you look at the corresponding mathematical problem, saying that the duration of the signal is limited means that I have a function which has compact support in time, okay? And saying that the range of frequencies is limited is telling that the range in momentum space is also limited. But we know from elementary analysis that if you have a function with compact support, its Fourier transform is holomorphic, so it cannot have a compact support. But what Slepian and his collaborators did, they studied this pair of projections, the one I just talked about. Okay, they took different values for the space cutoff and the momentum cutoff, but okay, this has no relevance. So I mean, what we do, we take the Fourier transform, which is the one dictated by number theory, which is this exponential here, and we take the projection in space and we take its conjugate by Fourier. And we look at these two projections all together. Now, when you look at two projections all together, it's not a difficult thing. Why? Because a pair of projections is just a representation of the dihedral group. Namely, if you have a pair of projections, you have a pair of unitaries of square 1. And when you consider a pair of unitaries of square 1, like U1 and U2, you know, what you can do is you can write in the group, you can write words, but I cannot repeat U2 after. Here, I have to put U1. And then I can put U2. And then I can stop with U1 or I can stop with U2. But that's essentially all I can do. So what happens is that, you know, you have this word, U1, U2, which is repeated, and it forms a group, which is Z. And then it turns out that the entire group is simply a semi-direct product of this by the group Z mod 2Z. So the group is very easy. It's essentially abelian. And when you apply the Marquis theory of, you know, of induced representation and so on, you immediately get that irreducible representations are in fact at most two-dimensional. And what they are, they give you the following situation. The situation is real, actually. So you have a two-dimensional space. The first projection will be the projection on the x-axis. And the second projection will be the projection on something which is tilted with an angle alpha. And you can compute the angle and so on. So what happens is that when you are in Hilbert space, infinite dimensional, of course you don't have a single angle, you have an operator angle. And this operator angle is best described as an element which commutes with the two projections and which is P1 minus P2 squared. Okay, all this is very simple. And what Slepian and his collaborator did in several papers, very interesting papers, I mean, you know, where they are conscious of the fact that what they have discovered is something great. And so if you want, what they have done, they have computed the eigenfunctions and angle for this pair of projections. And I mean, I will come back later in the talk to their main discovery, which is a differential operator which commutes with the two projections. But you don't need that for the time. What is important for the time is that you have this pair of projections and you can compute their angle. And you can compute, if you want, the eigenfunctions for this angle operator. These eigenfunctions are called Prolate wave, spheroidal wave functions. And what is important then is that the cosine of this angle between these two projections, if you want, amounts to understand a compact operator, which is the compression of the Fourier transform by the projection P lambda. Because when you square this operator, you will obtain the cosine of the angle between the two projections P lambda and P lambda at. And this operator is, you know, Hilbert-Schmidt operator, which is easy to write down. The reason why it is crucial for the computations that Slepian and his collaborators did, that they found a differential operator which commutes with it, is the following. The reason is not that it simplifies computation, it's that it makes computation at all possible. Why? Because when you consider this operator, it turns out that its eigenvalues, there are a few eigenvalues when it takes the square, which are very close to 1, so this means the angle is almost 0. Then they drop, and when they drop to 0, so the two projections are almost orthogonal, the speed at which they go to 0 is inaccessible to the computers, which means that you could never know which eigenvalue you are talking about, and you could never compute the corresponding eigenfunctions. So, but when you consider the differential operator which commutes with them, then it turns out the eigenvalues are very simple. They grow naturally, like pretty much like an arithmetic progression, and then you control what happens. So so this is the reason behind, the effectiveness of their discovery. But as far as the angle is concerned, this is okay, and this is the way, if you want, this cosine square of angles is depending on which eigenvalue you take. So and the mu, of course, mu is equal here to lambda square. So it's a square or lambda square because I took a small lambda. Okay. Okay. So I mean, typically this cosine square, look at what it is here. I mean, it's essentially almost 1. So what does this mean? This means that even though these two projections for mu equals 3.8, I mean, for lambda rather small, even though the two projections don't intersect, this is forbidden, they almost intersect. So this Prolate function, which is the eigenvector, if you want, for this pair of projections, is essentially in both of them. And in particular, this means that this projection is very well localized in space, but it's also very, very well localized in Fourier. So then you can look at the next one and so on. And of course, I mean, the next one and next one and next one, they will have the same property, but less and less somehow, of course, because they will correspond to values of the cosine, which are a little bit further and further than 1. Okay, so that's what you get. That's what you get. And I mean, these are these functions which are involved. Okay, so it is these Prolate functions which are involved in the formulas that we had obtained with Katia for the veil functional. Okay, so what we had obtained was this formula, if you want here. Yeah, this formula where we had all these Prolate functions which were entering. Okay, of course, after doing this work with Katia, we said, well, the next step is clear. Okay, the next step should be to now go to include the primes. And the first thing that we did in order to be able to include the primes was to show that the projections, the analog of the projections P lambda and P lambda hat, which exist when you put in the primes, also have the compactness property. However, what we did then also was to say, okay, why don't we compute directly with the computer the eigenvalues of the veil quadratic forms? So here we are talking about the veil quadratic form, okay, and okay, so you can, if you want the veil quadratic form now, what you can do is you can look at it. You can look at it on larger and larger intervals. The first thing that you can do, which is interesting, the first thing that you can do is to go beyond the interval which was between 1 over square root of 2 and square root of 2, which when you take the logs, okay, is something like that, okay? And already, I mean, for the first interval, you find the small eigenvalue, which is this, but this we could control with the computer, okay? So now you look at what happens when you use the same formula, but you don't include the prime. And what you find is that then it turns negative, okay? And it's only because you include the prime, the contribution of the prime 2, that it stays, the blue thing stays positive. The red thing is if you miscalculated, if you didn't include the contribution of the prime, okay? So this is a very, very precious information because it tells you that positivity has to come from other stuff, okay? And but the most striking information that we got is that when you compute these eigenvalues of the veil quadratic form, they are incredibly small when you increase beyond the interval coming from the Archimedean place. and when you go beyond. So what we found, with Katia is that, for instance, when you take lambda square, so the mu, so this is the mu of before, which is equal to 11, okay, then in fact the smallest positive eigenvalues is something like 10 to the minus 48. What does it mean? It means that, okay, it will be extremely difficult with the computer to prove positivity when you go at this, okay? But then we understood with Katia that the presence of these minuscule positive eigenvalues had an explanation, conceptual explanation. And it was explained conceptually, in fact, by the original construction of the absorption spectrum, because, in fact, we knew from the absorption spectrum that the Weil quadratic form has a radical. When you consider the Weil quadratic form on the full functions, it has a radical. Why? Because then you realize the spectrum as by the quotient by this radical. And this radical is obtained by the range of the map E. Now, the map E appears at first to be very, very mysterious, okay? On the other hand, if you think a bit, you will see that this map E is simply a Fourier transform in a way of the multiplication by zeta. And it's only now recently that we understand its cohomological meaning, as I said from the start, as Hochschild homology and the trace map. So this map E is there, it gives you the radical. And because it gives you the radical, I mean, it tells you that, you should have, normally you should have a zero eigenvalue. Why? You cannot have a zero eigenvalue because you restrict your functions to have, for instance, support between, I don't know, 1 over square root of 3 or and square root of 3. So the reason why you don't have a zero eigenvalue, even though you have this function, is that you cannot have, if you want a function of this form to have support between here and here. What happens is that if you take your function f to have support here, then what will happen when you make this sum? Because this sum, I mean, rather, let me take a function which has support, an even function, which has support between minus square root of 3 and square root of 3, okay? Now, what happens is that when I consider this sum here, of course, the corresponding function, because I multiply by n, it will vanish above square root of 3. So it will have support between, when I restrict it to the positive, between 0 and square root of 3, okay? But now the difficulty is that now what you want also is that this function, this sum here, should have support between 1 over square root of 3 and infinity to have the correct condition to be there. And in order to do that, what you have to take your function to be in p lambda hat. Because if the function is in p lambda hat, when you apply the Poisson formula, you will find out that the function of x inverse corresponds to the Fourier transform, and then it has the same property. But the problem is that there are no functions which are between p lambda and p lambda hat, which are in both. But we just saw that there are functions which almost do that. Okay, okay. So in fact, okay. So here I showed you the previous thing. Okay, and the small eigenvalues. So in fact, what we did with Katia was first to look at the eigenvectors corresponding to the very small eigenvalues. Okay, so this can be computed with a computer. You can look at what they look like, okay, and they look like that and so on. And then we got the idea of realizing the same vectors abstractly, conceptually, using Prolate functions. And so what we did, we took the Prolate functions, which correspond to the correct interval, as I was talking before, and then we applied to this Prolate function the map E. Okay. So as I said, we apply the Poisson formula, and what it tells us is that, well, if the function is almost in the intersection of the projections p lambda and p lambda hat, then okay, it will essentially define for you a function which has support between lambda inverse and lambda, and which is in the radical. Of course, it cannot be exactly true. In fact, one can prove that if you restrict the Weil quadratic form to the functions which have support between lambda inverse and lambda, I mean, there is no radical. There is no radical. This is just because of the holomorphic function theory. So what happens is that then we constructed an orthogonal projection using this construction, using these functions, and we were amazed to see that they reproduce exactly the eigenvectors computed with the computer, which were the very small, eigenvectors for the extremely small eigenvalues of the Veil formula. Okay, so I mean, this is done, so this is a fundamental fact that we discovered, which is that the space of eigenvectors of the k lowest eigenvalues for the Veil quadratic form correspond to the Prolate projection. So this is the second place where the Prolate functions play an absolutely crucial role. And I mean, the way we checked it is with the computer. And so when you see these various graphs, which are here, the fact that you see only one graph is telling you that the eigenvector which has been constructed using the Prolate functions is the same as the eigenvector which is obtained by the computer by looking at the Veil quadratic form. And of course, here we have the primes. I mean, we have higher and higher primes. Okay. And so, I mean, for instance, as I said, for mu equals 11, the eigenvalue is like 10 to the minus 48. So we keep going and we try then to compare more eigenfunctions. So here I look at the second smallest eigenvalue for the 16 values. Okay, and they still fit. But of course, if you go to higher and higher eigenvalues, I mean, like the third smallest eigenvalue, then there begins to be some disagreement, which is perfectly normal, because the agreement should only be for mu large enough. Okay, so they begin to agree around mu equals 4. And then, okay, I mean, here you can see that you have strong disagreement for the first values, but after a while, it begins to agree. Okay, so, and then, okay, with Katia, so we looked at much further, okay, what happens. Then we had a crazy idea. You know, it's what I would stress, really. It's very, very important from time to time to try a crazy idea. Of course, when you have a crazy idea, you also need to have the computer around. Otherwise, you could get absolutely nowhere. So the crazy idea that we had with Katia was the following. You know, after all, I mean, if you want, the minuscule eigenvalues of the Veil quadratic form should be discarded, and they are like the map E. So we are like working in the co-kernel of the map E because we want to discard the very, very small eigenvalues. So then we should try to construct a spectral triple which takes this into account, but is otherwise extremely simple. Namely, otherwise it's just the differentiation on the circle. Okay. And what you do, you take the differentiation on the Dirac operator on the circle, but somehow what you do is you condition this Dirac operator by this projection on the Prolate functions. Okay. So if you want, what we do, we take this interval, lambda inverse lambda, where we tested the Veil functional. We make it periodic. This is very artificial at the moment. We make it periodic. Okay, we take periodic boundary conditions and we condition by this. And we try to see what happens. So we compute the spectra and we look at them carefully. And okay, so we tried, you know, and I mean, okay, so we tried for values of mu, which are between, essentially between 6 and 16. Okay, and I mean, of course, it's quite important to look at the value of the cosine of the angle and to look at the good angles, but then we don't know exactly where to stop. I mean, how many conditioning we shall put. Okay, so when you look at 5.5, you begin to look, and okay, you find something which is rather surprising, because when you compare, if you want, these eigenvalues with the values of the zeros of zeta, it's quite nice to see that even this extremely rough conditioning that you do gives you a first eigenvalue which is like 14 and so on and so forth. So I mean, you know, it's not so bad. I mean, it could have been much worse. I mean, after all, you're just doing something, you know, incredibly rough, which is conditioning by these Prolate functions. Okay, and then you keep going. Okay, so I mean, you keep going and you keep comparing the values of the zeros of zeta with these values. Okay, and you know, it sounds sort of encouraging. Okay, so you keep going and so on. So I mean, we did this calculation for a long time. We did this calculation, And you know, I think I said, I think last year it was in my talk in a Piotr seminar, that it was like we found out that there was a kind of devil which was making fool of us, because you know it was resembling. I mean, there was an obvious resemblance, but there was never anything like you know, very precise agreement between the two. I mean, you know, there was an obvious. It was always looking like, but you know, never something which was a precise agreement and so on. So we kept going, you know, 9.5, and then I will show you 10.5, which was nice also. I mean, you know, okay, so we did that, and then almost by chance, okay, we use the computer to compare, to see what happens when you change, when you alter the number of conditions that you use for the conditioning. A priori, okay, one can estimate this number of conditions that you use for the conditioning. Okay, this is where it relates to the Riemann-Siegel formula. But you can never be sure. So what we did then, if you want, was to compare the conditioning with 2L with the conditioning with 2L plus 1. And what did we find? We find something this time which was really amazing. So what we found is that, for instance, if you look at the behavior of the first eigenvalue, and if you condition with like 2L, you get this blue curve. If you condition with 2L plus 1, you get this other red curve. And of course, in general, they don't agree at all. I mean, there is no reason, because you add one more condition. But sometimes they agree. And when they agree, like here, you know, the value that you get is on exactly the corresponding zero of zeta. Of course, you know, this could have been an accident, so we tried for the second eigenvalue. And what we found for the second eigenvalue is, paf, exactly the same thing. So that when they agree, they, first of all, they always agree on the same line, you know, and this line is corresponding to the second zero of zeta. Okay, so we did this calculation very far. Okay, fourth eigenvalue, for instance, and so on. And then we use this criterion, namely the coincidence of eigenvalues, to now get, if you want, show off of what we get as a spectrum as compared to the, so this is the zeta, and this is what we get by this comparison. And you can see we were not quite happy, because, for instance, here, okay, these two guys were a little bit too close. So we said, okay, there is something we don't understand. So we kept going. And I mean, there is a nice way, if you want to represent what I just said, which is by the evolution of the eigenvalues. Okay, so then if you want, what happens is that you can now look at the corresponding eigenvalue and the way they behave as a function of the lambda. And what you find out is that, I mean, there are places where all these curves touch each other, which is quite amazing. So all these curves actually, and when they touch each other, the value is the correct one. So here is the corresponding zero of zeta. So we were sort of mystified by these facts. And then we had the idea also of comparing not only with what happens when you do the conditioning, but also what happens when you look at the spectrum of the original Dirac operator. Okay, so and this came from the fact that if you want, there turned out to be for these points of contact, whenever there was a point of contact, we noticed that it was satisfying a quantization condition, because a point of contact, like here, if you want, it has a coordinate x and a coordinate y. And all these points of contact were satisfying the quantization condition, which is that x to the power iy is equal to 1. So this was kind of experimental. So then what we did, if you want, was to compare them with the graph of what you would get without conditions, and they meet. They meet. If you want, here you add one more, they meet one more. Here also they meet, and so on. Okay. And finally, we understood what was going on, which is the following. Which is that, if you want, what happens is that this quantization condition is fulfilled by the eigenvalue of the original Dirac operator. And what really happens is that it can happen that an eigenvector for the original Dirac operator is an eigenvector for the conditioned Dirac operator. And this led us to a mathematical theorem and a mathematical understanding of what was going on. But especially, I mean, the first thing that we did was to reobtain the comparison. So here you have zeta, and here you have what we computed for the 31 first eigenvalues. Okay, and now the agreement is really perfect. I mean, now there is absolutely no discrepancy whatsoever, which is occurring between the two. So what we discovered with Katya is the conceptual explanation of this coincidence, if you want. And the conceptual explanation comes from the map E again. And the map E is understood, if you want, by the Riemann integral. So, so when I was talking about the map E, I was taking the sum of f of nx. But this is a Riemann integral. I mean, this is an approximative Riemann sum, if you want, for the Riemann integral. And what happens is that we get an abstract notion. We get an abstract notion, which is the notion of a zeta cycle. So a zeta cycle is something very, very simple. It is a circle of length L. Okay? So it's a circle with the ordinary metric. And what one assumes about this circle is that when you take the Riemann sums but rescaled, made scale invariant by taking sum of the powers of mu applied to the variable, okay, you assume that this subspace of Riemann sums is not dense in the Hilbert space L2 of the circle. That's what we call a zeta cycle. Okay, so it's a very simple notion. It has to do with Riemann sums. And our main result with Katya is the following, is that these zeta cycles are exactly ruled by the zeros of zeta. Namely, if you take a zeta cycle, and if you look at the action of the multiplicative group on the orthogonal complement of this subspace in L2, then it's formed by imaginary parts of zeros of zeta on the critical line. And conversely, if you have an imaginary part of a zeros of zeta, you get a zeta cycle. So if you want, this theorem, it provides a theoretical explanation for the above coincidence of spectral values. And what it explains, if you want, why the low-lying part of the spectrum, okay, of this spectral triple was possessing this resemblance with the low-lying zeros of the Riemann zeta function. I mean, this becomes very clear once you have this theorem. But it is also very tantalizing because of the following fact, that if you take a zeta cycle and if you take an n-fold cover of zeta cycle, it's also a zeta cycle. So it suggests something which is still totally mysterious, which is that zeta cycles should be related to closed geodesics. Because of course, if you have a closed geodesic, you know, you have this n-fold cover, which is also a zeta cycle. Okay. Now, if you observe the spectra, which I showed you before, I mean, you know, if you not this one, of course, but if you observe the very basic spectra that I showed you before for all these values, I mean, not this one, but not the one before we got the key, but yeah, what you will find out is that, you know, this is the spectrum that you get for this Dirac operator. And what you find out is that after a while, it looks like the spectrum of the unperturbed Dirac operator. So there is no chance whatsoever that it can agree with the zeros of zeta. Why? Because the Dirac operator, which has been perturbed, when you count its number of zeros, you know, the number of zeros less than E, it will always be linear in E. Okay, and this is because we took periodic boundary conditions. Now, so there was an immense issue in this stuff, which was to guess, if you want, how one could handle the ultraviolet behavior of Riemann zeta and then try to combine it with what was found. And for zeta, okay, so this is joint work with Henri. For zeta, it's very difficult. Why? Because the number of zeros, you know, it's not like a linear in E. It has this log term, and then it has plus a term in O of log E. So, I mean, it's very subtle. It's very, very strange. And I mean, by really by, I would say, serendipity, we found with Henri the answer. And the answer comes from the operator that Slepian and his collaborator found, which is the Prolate spheroidal operator. I will be very fast on it because, I mean, there is this beautiful talk by Harry a week ago, and I want to reach the point. So, I mean, this operator has amazing properties that it commutes with p lambda and p lambda hat. And the reason why it commutes with both is that, it's very strange, first of all, that a differential operator should commute with a projection, which is, a discontinuous function. After all, it's a characteristic function of the interval minus lambda lambda. But on the other hand, okay, I mean, x dx commute with a characteristic function of 0 infinity, because this is a generator of scaling. So this is not so hard to understand. And when you take this operator, it commutes indeed with this characteristic function. And why does one get an operator which commutes with a Fourier transform? Because one makes this operator Fourier invariant. This was done by these guys, okay? And you make it invariant by adding a term which is a multiplication by a function. And so because it's multiplication by a function, it will not spoil the commutation with p lambda. And because now it's invariant under Fourier, it will commute with both. So, I mean, all this is simple. All this is simple. And I mean, behind this, so, I mean, this operator, I mean, I won't repeat the fact that this operator was known in the 1930s already, because it had appeared in a different perspective. It had appeared in the diagonalization of the Laplacian on the Prolate spheroid. So let me skip that. Okay, let me skip that very fast. But one thing I still want to mention is that this operator, is very well understood as an element of the enveloping algebra of the Lie algebra of SL2R, because you have a representation of SL2R. I mean, this is what I learned from Rico. You have a representation of SL2R which is preserving even functions, which is given by this multiplication operator, this differential operator. And when you consider their commutator, you find this operator here, which is such that essentially its square is a Prolate operator, except that you have to add the Hermite operator, which is a combination of E plus and E minus. Okay, which is this. Okay, so I mean, let's keep this in mind, but let me come to the point. So when you come to the point, okay, what you find out is that somehow now this operator is kind of resolving the issue that we had with Katia, which was that the quadrant, this piece here was not invariant under the scaling, because now this quadrant is invariant under the Prolate operator. The Prolate operator is not scaling, but it's very close, okay, because it's very close to the square of scaling. And what one can begin to do is to do semi-classical computation of the number of quantum states which are governed by this operator. Okay, so one can do that, and we did that with Riku, and to our amazing surprise, we found this term E over 2 pi log of E over 2 pi, as in Riemann, plus additional terms, okay. And I mean, okay, it uses, Legendre elliptic integrals and all sorts of stuff. And I want to skip also this part on the Liouville transform. I mean, then by using deep results on the control of the eigenvalues of a Liouville operator, then we were able to refine the semi-classical approximation, which is very rough, and to obtain now, if you want, the fact that one will get for lambda equals square root of 2, one will get the correct the correct behavior, like in Riemann, and with a log term with a capital O of log E term, exactly like in Riemann. Okay, so we did these calculations, and then we asked the following. Of course, this operator is like a Laplacian, and one has to find the corresponding Dirac operator. So, I mean, as I said, Riku has explained very much in detail how we got to this Dirac operator. And I mean, it's quite tricky. The Dirac operator is obtained by using a method which is called the Darboux method, but in fact, it's not due to Darboux, it's even older. So it's 19th century stuff. And what it does is to factorize an order 2 operator, pretty much like a Liouville operator, into a product of two order 1 operators by solving an associated Riccati equation, which is here, which one can solve. The solution is not unique. It depends on a modulus, which is a complex parameter, which is in the complement of the real line in the projective complex plane. And for each of these modulus, you do get Dirac square root of the operator, okay, by solving this type of Riccati equation. And now what you have is you have the fact that the square, all these operators are isospectral, so their spectrum doesn't depend on the choice of the modulus. And you have this equation, which tells you that the square is like 2 copies of your original Laplacian. But what is the most amazing and was depending most work was the fact that the number of purely imaginary eigenvalues of the Dirac operator is exactly like in Riemann zeta. And it also has real eigenvalues, and they correspond to the trivial zeros of zeta. I mean, Riku explained that in great detail also. So what I want to show you now is, somehow in this stuff, I mean, one could also always make mistakes. I mean, there is no warranty whatsoever, except when you do the computer calculations. So I want to end by showing you the type of computer calculations and the comparison with the zeros of zeta for the ultraviolet stuff. So, I mean, the calculation is done as follows. What you do is, you want to solve, so this is for the operator W lambda. You want to compute its spectrum. You want to compute the negative part of the spectrum. Okay, and what we found with Riku is that the negative part of the spectrum is discrete, so it's a discrete spectrum. It has this growth, as I said, and moreover, it corresponds to a boundary condition. So there are two boundary conditions. I mean, to understand what happens for even functions, you can look in the interval, which is from lambda to infinity. Okay, and we take lambda equals square root of 2. And there are two boundary conditions. There is a boundary condition here, if you want, at lambda, which is regularity. But there is a condition which is much more tricky at infinity. So at infinity, it means that essentially it's something like a sine over x, the behavior at infinity. So in order to compute the spectrum, what you do is you take the solution which is regular, you take the solution of the eigen function, eigen equation, which is regular at square root of 2. You prolong it using the computer. You take the solution at infinity, which is in the correct boundary condition, and it's known that it's Borel summable and that it has an asymptotic expansion. And what you do is you compare the asymptotic expansion at infinity with what you get from the regular solution at square root of 2. And when they agree, you are done. Or when they are opposite to each other, you are done. You have an eigenvalue. So you look. Okay, so this is a typical example for minus 38. You have an eigenvalue because these two guys are exactly opposite to each other. Okay. And for instance, now for minus 33, so these are the negative eigenvalues, you look at these two guys, they are the same. So you have an eigenvalue again. And you keep going like that. For instance, for minus 150, you have another eigenvalue because they are opposite to each other. Okay. So now with this, you plug in these eigenvalues. Okay, fine. I mean, you cannot be too precise with them. You just plug them in. Okay. And they are all negative. And now you compare 2 square root of minus z. This is what happens when you change variable to the Dirac with the zeros of zeta. And this is what you obtain now. Okay, this is what you obtain. So you obtain this comparison. This comparison goes very far. Oh, now you can go very far. You are no longer periodic in one way, and you couldn't compare with others. You can go to infinity. Okay, and when you compare, in fact, you can plot the nth eigenvalue of the Dirac compared to the nth zero of zeta. And this is the type of stuff that you obtain. So for instance, here, you see only one red dot. this means that the two values agree. And so here is for the first 30 eigenvalues, but you can keep going to the first 60 eigenvalues. Okay, and you can even go up to the 100 eigenvalues. And what you see is that by doing this, we have been able to catch the ultraviolet behavior of zeta by this prolate operator. This prolate operator, which is very related, if you want, to the scaling operator. It's like the square of the scaling operator, except that now you made it to commute with the cutoff. You made it to commute with the restriction to the quadrant, okay? Because it commutes with the projections, with the two projections. Okay, and this, of course, for non-commutative geometry raises a really great problem, which is to understand the associated geometry, because the Dirac operator is acting on a space which, to simplify, it's like lambda infinity. But it's good actually to include in it also the interval minus lambda lambda, or anyway, these are even functions. Okay, so it's good to include everything and to look at what geometry we have. And when we look at if you want, the symbol of the operator, symbol of its square, which is given here, what we found is we find what is the corresponding metric. So that's clear. And what we find is that this metric is very subtle, because on the interval lambda to infinity, it is positive, because I have so it's negative here, it doesn't matter. And in the interval from minus lambda lambda, it changes sign. So this means that the metric, the signature of the metric is changing. Okay, and what we found with Henri is that in fact this metric is very directly related to the metric in now a two-dimensional Minkowski space, which is normal because there is this change of sign, and which is the metric of a black hole. So there is something very important to explore from the non-commutative geometry point of view. Okay, of course you can change the thing and so on and so forth, but the thing which is really fundamental to explore is the spectral triple now corresponding to the ultraviolet behavior, not and to try to combine this spectral triple with the spectral triple I had constructed with Katya for the infrared behavior. And I want to end by showing you the picture of the black hole embedded. This is embedded now in Minkowski space. Okay, so you can compute an embedding using elliptic integrals again in Minkowski space, and the computer will give you this picture. And in this picture, what you will see is that there are these geodesics which are whirling, in the horizon of the black hole, but there is this straight line which is our geometry, okay, and which, of course, obviously is begging for a much better understanding than what we have. Okay, so I think I will end here. I will end my talk.
Thank you.
Yes.
Very nice. So thank you for being in this finite time interval.
Yes.
Great.
Yes.
So are there any questions?
Sorry, I have a question. You mentioned that this map calligraphic E is somehow related to the Hochschild homology.
Yeah.
Could you somehow elaborate more on this?
Well, this is the paper that we are writing with Katya, so I'm a little bit, reluctant to, but it is. If you want, the situation is very similar to the following situation, that there is so if you want, the first spectral realization as an absorption spectrum revealed the geometry which is behind. But it did not reveal yet the nature of the vector spaces that were involved. And what we are discovering with Katya is that the vector spaces involved are best understood from Hochschild homology. That's the essence of it, if you want. And that the map E is just a trace map in Hochschild homology, which means that now we really understand what it is. I mean, at the start, you know, it was totally mysterious and totally non-geometric, but now it begins to be really geometric. So I mean, this is something that we write for the proceedings of the cyclic homology conference at the Fields Institute, because it relates really to Hochschild and cyclic homology, which is very important, of course, in this respect. The reason why, if you want it, it is important to use Hochschild homology and so on, is that as a quotient space, the Adel class space is related to a non-commutative algebra. And for a non-commutative algebra, the replacement for differential forms is Hochschild homology. So that's the essence of what we are doing, if you want.
Thank you.
I also saw Teun.
Yes, I have a bit of a hypothetical question because I want to know what the next step is. You have this Dirac operator whose eigenvalues very closely resemble the series of zeta. But if, for instance, if you would have a bounded perturbation or a relatively bounded perturbation in the sense of Kato relief, which would in fact give you the zeros?
Yeah, well, okay. No, your question is excellent. Let me answer in detail. You see, what one wants to have, okay, I mean, one can have demands which are more and more, I mean, difficult, but the demand which seems to me the most reasonable at the moment is to have something which is exactly like what we did, okay, with Henri, I mean, with the ultraviolet, but taking in account now finitely many primes, which is what we were doing with Katia, because in what we were doing with Katia, we were taking the integers, which were, you know, giving you the restriction of the map E to the finite interval, and these were already involving the primes. Now we know what is the Hilbert space setup in order to do that. The Hilbert space setup is the one that I had in my original paper for the semi-local trace formula. So we know what is the Hilbert space setup. What we do not have, okay, in this Hilbert space setup, there are the projections P lambda and P lambda hat. Their product is still a compact operator. That's what we proved in the paper for the quasi-inner functions using holomorphic functions. Okay, but what we don't have is the analog of the Prolate operator. And the conjecture is that when you will look at the corresponding Prolate operator, it will be what you suggest, namely a kind of bounded perturbation, you know, of the one we found with Henri. I mean, the fact, if you want, that you will involve the primes will be relevant, but will not be impossible, in the sense that when you consider p-adic numbers, there is no problem of having functions which have compact support and whose Fourier transform is compact support also. There are plenty of such functions. So if you want, the essence of the problem is already at the Archimedean place. The full essence of the problem is there. And so, I mean, the next step would be, as a possible next step, would be to extend this framework to involve finitely many primes. And then gradually one will get better and better approximation. This is the idea.
Okay, thanks.
Okay, I saw Reimer, but I'm not sure if that was correct. You have your hand raised. Otherwise, someone else. So maybe one question from my side on this extension to R2, Alain. So you have this time coordinate that you add, but it seems like so why do you add it? Because it's you already have this kind of scaled metric in one dimension.
Yeah, sure. No, of course. I mean, the reason to add it is to have a Minkowski type metric of 2 dimensions. So, I mean, I add the time variable, and the beauty, if you want, is that you can make it periodic. So the fact that you can make this additional variable periodic, it's a kind of compactification, if you want, and you essentially, I mean, it shouldn't play much role. This is the idea. But the idea is that then you get something Minkowski 2-dimensional. I mean, okay. I mean, one can probably do better than that. I'm not advocating it but I mean, okay, it appears to be kind of natural. But okay, it might be that one can do better. After all, as you say, one has directly a spectral triple, you know, which is concerning a one-dimensional piece, which has the correct growth and so on and so forth. So this is what one should study, of course.
Yes,
But I mean, you could also have started with a plus, right? I mean, so what's the reason for introducing this minus alpha x dt squared? Is there a deeper reason?
Oh, no, the reason is to get a black hole. Yeah, sure. Yeah. No, of course.
Very good.
Right. One could add anything you want. One could add anything, sure. No, of course. No, but I mean, somehow, I mean, the black hole, because it satisfies, it has beautiful properties. So that was the idea.
Sure.
Yeah, I mean, in a way, okay, let me tell you what we would like to have, I mean, with Riku in that respect. I mean, after all, what we have found, without adding the time variable, what we have found is a kind of a cusp that Zellberg was looking for, if you want, because it has the right growth, I mean, of eigenvalues and so on. And okay, and now one should sort of naturally, improve on this cusp, and eventually, of course, put in all the primes, But okay, but that's where we stand. And I mean, the point though is that it's incredibly natural from the point of view of the original problem of the conditioning of the Prolate functions and all that. I mean, the thing which is to me most amazing is the fact that I had in 1998 the self-adjoint extension of the Prolate operator to the full line, and I didn't look at the spectrum, and that's what we started doing with Henri 1 year ago. So I mean,
Okay, thanks.
Yeah.
For someone else?
Yeah, I want to add to what Alain said something, namely, this Dirac is with coefficients in a bundle. This bundle, I mean, it's two-dimensional. So
yes, yeah,
so you expect that underlying space to be two-dimensional.
It's not like the Dirac on a one-dimensional manifold.
Yeah, exactly.
Yes.
Yeah, very good, Riku. Yes, yeah. It hints, to hidden the dimension. Exactly. Yes, yeah.
You mean also when you look at that spectrum, it's probably more two-dimensional than I don't know if it's two-dimensional.
No. The spectrum is really one dimension, 1 plus. You see, when you have E log E, what it tells you is that it has a double pole at the dimension spectrum has a double pole. Yeah, that's what it tells you. So it's one dimensional. No, it's like a cusp. It's really a cusp-like.
Okay, thanks. Anything else?
I maybe have just one quick comment that Henri's recording will be available, is already available on YouTube, and you will all get a link after this seminar.
Okay, good.
Thanks,
because it was mentioned, so you will get just immediately after we finish. I'll send you an email with a link to Henri's talk.
Okay.
Very good.
Okay. Well, thank you. Also, thank you all for coming, and and thanks to Alain again for this nice talk. And with that, I would say enjoy the summer and see you next year.
See you next year, guys.
Thank you, Alain.
Bye-bye. Thank you so much. Bye.
Bye-bye.
Bye.
Thank you all.